Hello, in this video we will talk about laser additive manufacturing, probably more widely known as 3D printing. In additive manufacturing we build up material according to the information directly from a computer. We call it digital photonic production, where we make use of a design which we have available in the computer as a corresponding data set and directly use it for the production without any further tools in between. In the overview of the lecture, we will find fundamentals of laser additive manufacturing and several examples. Historically, it all started with selective laser sintering, became selective laser melting. Laser metal deposition is a different powder depositing process, and ultimately I will talk a little more generally in the outlook on digital photonic production. So in the first slide you see a survey of some examples of additive manufacturing processes. Historically, in the beginning, stereolithography out of liquid polymers or laminated object manufacturing made from paper type individual layers, and the two in metal, which we will focus on later, selective laser melting and laser metal deposition. All of such processes have in common that they produce the part layer by layer. And in the subsequent slides we will focus on two of these processes, selective laser melting and metal deposition. So again, the key characteristics of the process are displayed in this very simplified process chain display. We start with a CAD model in a computer, then we slice the information layer by layer. This is more or less the inverse of what you may know from a computer tomograph, where you have a 3D picture and slice the information to look at individual cross-sections. So similar technology here. By using the sliced data of the individual layers, we then can print the part layer by layer and come up with the 3D reconstructed image that we designed in the first place. So the first process I want to look in more detail to is selective laser sintering and selective laser melting. In this application we again have the three-dimensional computer model which has been sliced into individual layer information, and we have a material powder, in this case a metal powder. So the process in detail works such that we focus the laser radiation onto a powder bed and the information is, so to say, scribed into the surface. Then we lower the platform a little, about a few tens of microns depending on the powder grain size, and add a new layer of fresh powder on top of that, and then the process starts again. We melt the next layer of powder to the lower layer of material, so that layer by layer we grow the part out of the powder. And as a consequence, as you see in this fantasy part on the right here, you can make very complex structures. This is cut open to look at and to take out the rest of the powder. So you see a scaffold, very complex shaped, which can be produced very difficultly only by alternative processes. So to look at the process a little more in detail, in sintering, usually we use metals or metal powders coated with some polymers. The polymer is molten and joins the metal particles, and then we remove that polymer and maybe we infiltrate some lower melting metal in order to get a compound, a metallic compound, but which ultimately will result in some metallic structure. However, we will have some pores remaining and it will be more or less a density pressure defined process from which we make some metallic prototype. This was actually due to the fact that the laser intensities and powers were not sufficient to make use of that full melting, so that in this case you had compounds and some remaining porosity in the processes. Nevertheless, it was very helpful because you were able to really make metallic parts. With the advent of high quality lasers, it was possible in the late 90s to develop an all-metal process, and this all-metal process was scaled and developed such that several materials and metals can be processed in selective laser melting. For instance, titanium alloys, aluminium alloys, steel, cobalt, chromium, ceramics, biocompatible, bioresolvable materials, a lot of applications which have been developed in this context with the simple scale and scheme of placing one layer of molten material onto the next one in generating these parts. To illustrate the process, I show a video in which you can see the process in more detail. This is the deposition of a powder layer. Then it's flattened, and then the laser scribes the information into the surface, melts the material where the part shall be generated. Then comes the next layer of powder, next illumination, and layer by layer, in this case here it's a conformal cooling component of an injection mold tool which is produced, and then we take away the powder which has not been used, by the way, which is regenerated and reused. So we can make individual parts, we can make very complex parts. These scaffolds or lattice structures are no additional effort, in this case for medical implants in the spine, which are examples how this very complex, capable process is used. Just one word on the terminology. Actually, there have been many names for the same process, depending on the culture of the industrial origin of the process or the machine. So, for instance, the colleagues from EOS call it direct metal laser sintering. SLM Solutions calls it selective laser melting. Trumpf calls it laser metal fusing. Direct metal printing, selective laser metal printing, is metal additive manufacturing, laser cusing. There's just one international standard so far, which refers to as laser powder bed fusion. Nevertheless, laser selective melting, selective laser melting is also used quite frequently. Some applications. I showed you this fantasy part already for demonstration of the possible complexity. If you get serious about that, of course, then you can design components. This is an automotive actual component. It's a suspension connecting rod. And you see it, yes, is a scaffold type structure which is designed for maximum torsion and stability. However, we can also develop it according to lightweight design by really using very thin gauges and enhancing the interior with a microstructure, such a lattice structure as you've seen it here in this cut open part, example part. And in doing so, we make use of what we know from biology, because you may know from bones that they carry kind of a spongiosa inside of the bone, which are these tiny bone bridges which guarantee a very high stability and simultaneously localized flexibility of the part. An early application is shown in the left, individual implants for teeth, which have been developed and marketed with the beginning of the century in the very first days of the 2000s. Just a word on the performance of such structures. Of course, you have to be sure that you have density 1. So we talk about density 1 as soon as we exceed 99.99. So you always have a little rest porosity, but in this area, it is very comparable to casting or other metal producing processes. If you look at the mechanical properties, ultimate strengths, yield strengths, breaking elongation, then you see the performance here in the bars, and in the lines you see the corresponding Dean values for the individual properties. Green is the ultimate strengths, blue is the yield strengths, and the breaking elongation is the gray. And you see in all instances we are well above the limits which are given by the corresponding norms. So that can be even increased. We can even get more higher values by corresponding resolidification tailoring. So if we adjust the solidification by the knowledge of the metallurgy, we can tailor the properties in terms of these mechanical behaviors and characteristics, also locally to the individual part. That's really unique, and you won't find that with any other production method. Of course, the question is, how can we scale that to higher productivity? And there are several concepts. One of them is a so-called skin core concept. It's like painting a painting. For the larger areas, you use a bigger brush, higher power, wider focus, and scan the material surface very fast with high powers. And in the skin areas, in the boundaries, you use fine brushes, so to say, in the metaphor, and you have very focused radiation in order to get high precision of the edges of the part. Skin core technology, which leads to scaling factors of productivity about up to 2 or 3. The next process I would like to discuss is laser metal deposition. In this case now, as you see in the right scheme, we don't use a powder bed, but we use a powder jet. We also talk about powder fed 3D printing or additive manufacturing. In this case, coaxially to the laser beam, a powder jet is suspended on the desired geometry, where we build up again layer by layer, now more or less writing, like I do with my pointer here, writing layer by layer on top of that structure. In this case it's simply a square. On the left you see some examples of trials for slants. So we can slant the geometry, we can change the direction, the angle up to certain degrees, certain angles. This is possible. On the right now you see a picture of the process. It is quite nice to see the coaxial powder flow and the interaction zone with the laser, which coaxially comes through that nozzle and melts the powder just at the point of interaction, or the tool center point. If we look at the process in more detail, of course we have the deposition of the laser energy, the absorption in the powder, the melting process, and then of course the heat conduction. If you look at it in more detail, then of course it is obvious that we need to adjust the speed at which we deposit the energy, so the energy deposited per time and length, such that we get more or less constant temperature on the surface. There will be heat accumulation at the edges, which we can take care by reducing the laser power or increasing the speed. As a result, then we can get rather homogeneous buildup of such layers. In this case, on the left, you see an example. This is only 0.5 millimeter in width. So it can be amazingly precise. However, of course, in most or practically all of the applications, the edges will be defined by resolidified melt, and this is not sufficient for applications in general, so we need a milling process after that. But we mill away only a very thin layer, maybe just a few tenths of a millimeter to get to the final shape. An example is shown here in a so-called blisk. A blisk is a blade integrated disc. Turbine blades are made usually with individual blades for exchange. However, it is much better to have monolithical structures if one would be able to repair the wear of such discs or such blades on discs. And that's why people built the so-called blisk. And these blisks today are regularly manufactured and maintained. Maintenance is done by laser metal deposition. In this video, you can see the process. So it starts with the first layer on the individual blade on that disc. So the disc is cast. That's pretty quickly done. And the more complex parts then are added with laser metal deposition, layer by layer. In this case, you make use of the fact that you have to build up many of such blades, and you do one after the other, layer by layer, to allow the previous one to cool down for the next process. So that actually concludes this short introduction to additive manufacturing. And in the outlook, I would like to put emphasis more on the economical and the scaling effects of such processes, because they will have a significant impact in our production world if we are able to scale that process. So the structural characteristics of the process are displayed here. If you look at cost versus lot size, usually you are aware that the more you make of a kind, the less expensive it gets per part. This is classical manufacturing technology. However, if we look at laser processes, we realize that it is very different, because we have in first order no dependence on the lot size. If you think about laser cutting, it doesn't make a difference if you cut one part or 100 parts, considering the cost per part, because you do it subsequently. The advantage is there is no lot size dependence on the cost. However, the cost is pretty high. So it will only make sense for rather small lot sizes. So the challenge and the task for the future must be to bring down this curve in order to increase productivity and shift the crossover of the laser manufacturing line with the classical manufacture line to higher lot sizes. And it's fair to say that presently there is an achievement that series production has been started at lot sizes of several tens thousands of pieces. So at this domain already we face the use also in higher lot sizes in additive manufacturing. The next advantage, of course, is the complexity, which is for free. You have seen that in the demonstration parts quite clearly, I hope. So usually in conventional manufacturing, again, the cost of a part increases with product complexity. And as you've seen, not so in digital photonic production, in additive manufacturing, but also in other laser applications like laser ablation, drilling, or even cutting, where we have no dependence on the complexity because we have no tools. And again, same thing, if we want to increase efficiency, what we do is we reduce the cost, and so we shift again the crossover to points of lower product complexity, which means it doesn't make sense only in very complex products, but now it makes sense also to use it in more simple products. So to summarize, in the beginning of the technology, we had use of the technology only in rather individual cases, that's why it has been referred to as rapid prototyping for many years. And also it made sense only to be applied at rather complex parts of high complexity. But with the development of higher productive processes, people are able to shift this curve down, and now it is used in series production as well as for less complex parts. As a last characteristic, I would like to focus on the cost dependence of the weight reduction. Usually, cost increases if we want to reduce weight. We need to produce more complex geometries, combine materials, lightweight structures. So usually this is involved with more cost. If you think about additive manufacturing, especially selective laser melting, it is systematically not the case. The less material we melt, the less time we take to produce the part, and the less expensive the part will be. So a characteristic of this additive manufacturing process is that reduced weight is directly correlated with less cost. And this is amazing because, as you remember, complexity is for free. So as you see on the right hand side an example, we can make digital materials which are constituted from several, in this case, individual spheres or scaffolds. You can design whatever you want in this context. So complexity doesn't matter. The only thing which costs is the matter which is molten, so the weight of the product. So we have seen in this video all the possibilities and the challenges in scaling the productivity of additive manufacturing. We can see the scaling in different materials, even in material combinations, so to say color printers which can be built. And the ultimate vision, of course, will be to change also the thinking in the whole design of the product and the corresponding production chain. And that is the wonderful thing about digital photonic production, that we are able to design something very complex in the computer, press a button, and print the product.